What's up, my guys? All right, so today's notes, this is just going to be part of today's notes, and it's going to kind of be used to introduce the physical pendulum to a certain extent, so you're going to have another lecture on that. But really, this is just about number 10. It's quite an interesting problem, and it's a problem that I thought sort of deserved its own little mini video, so this might take some time, and certainly it'll help you. It'll more or less directly show you how to solve this problem, because it's the kind of problem where I really think we should go over this kind of as a class. So with that said, we're going to take a look at number 10. What number 10 says is that we have a marble, and the marble is placed at the bottom of this large bowl, and it is quite large, a half meter in radius, so you know what a meter stick looks like. So we got a bowl that's a meter across from edge to edge. Anyway, the marble is displaced slightly, and it oscillates back and forth. So you can just imagine this marble kind of going, back and forth. We've got this big bowl, and the marble just is one of these, okay? So it's not a very large oscillation. It's just a little oscillation, okay? And so what we're going to do is we want to find the period of that oscillation. And this is actually going to be somewhat of a challenge, okay? So we're going to go ahead and sort of try to understand this problem. So if we kind of visualize things here, right, we have this little marble, and it's going to be oscillating back and forth between these 2 points. And the bowl has a radius of half of a meter. So if we draw a line, okay, then we can see that this actually looks a lot like a pendulum, right? And you might be tempted to say, hey, well, I know the period of a pendulum, and it's actually really easy. It's just, 2 pi square root L over G. And that actually would work fine, except we have the problem of the fact that this marble is rolling without slipping, and that actually complicates things. So on a pendulum bob, the ball or the bob there is just, it's not rolling. It's just stationary as it's, relative to the string, it's stationary as it swings back and forth. This is not. Now, if you do this calculation, I do believe you get something along the lines of 1.4 seconds. And the reason I mention that is just because it's approximately correct. The correct answer is actually 1.7 seconds. So this isn't the worst way to do it. You actually get something that is approximately right, but it's not what we're after today. So we're going to do it the full way. And it's a very instructive problem, which is why I decided to make this video. So how do we approach this problem? Well, hopefully by now you guys have some experience and are comfortable with rolling without slipping, and that's kind of, where we're going to have to start, okay? So what do we do when we have rolling without slipping? Well, usually we do what we do with forces, and that's where we write, draw a free body diagram, we write net force equations, and we go from there. And don't forget, because it's rolling, we're also going to have torques, and so we're going to have to write a torque equation, right? So the first thing I'm going to do is draw the ball, marble right here, and this is going to be, let's say, wow, that's ugly. Let's just do that. This is going to be, actually, we're just going to do a circle because that's prettier. Yay! It's going to be while it's not at the bottom, okay? So we're not talking about down here. We're talking about over here and over here. So in particular, I'm going to take a look at the left side, okay? We're going to say it's over there on the left. Now, I want to draw a free body diagram, so I'm going to be concerned about net forces here, or forces, not torques, okay? So we have 2 forces acting on the marble. We know we have gravity, and gravity is down, but to jump ahead here, we're not actually concerned about the downward part of gravity. We're only concerned about the component of gravity that brings the marble back to the center, and that is the restoring force for this harmonic motion. And that restoring force is going to be inward like this, let's say, and this is mgx. And if you remember, when we're on the inclined plane as we are here, so to speak, this is actually not just mgx. We can calculate this as mg sine of theta, okay? And then the only other force acting on the marble, well, it's rolling, so there's going to be static friction. So I can draw static friction down here, and I'm just going to label that Fs. And static friction is applying a force to the bottom of the marble there. And so from a net force perspective, this is what's happening to our marble. Now, we can then note that the marble is accelerating to the right, and that's a positive sign there. And so the direction that is positive would be down and to the right. And so looking at that, we can write our net force equation, and I'll just write it like this. We have mg sine theta minus fs is equal to ma. Okay? So far, so good. Hopefully that makes some sense to our brains. Now, quickly, I can go ahead and also take a look at the torque acting on the ball. And that's pretty easy because there's only one, right? We have Fs acting on the ball that creates a torque. Remember, gravity cannot create a torque about an object's center. This object is rotating about its center, so gravity can't do a thing. So we only have net torque to worry about with the ball here due to friction. So I'm going to go ahead and use the radius of the ball times Fs. By the way, keep in mind we don't know the radius of the ball. We know the radius of the bowl is 1/2 meter. We don't actually know the radius of the ball. So this is not the same thing. So we'll call this one big R, and we'll call the other one down there little r. And then that's going to be equal to I alpha. So far we have two net force equations, RFS, and then we have I alpha, right? So hopefully that makes some sense to us, right? Now, note there are a couple hints on this. It does say to use the moment of inertia for a solid sphere, so that makes perfect sense, I think. We have a ball. It's a solid marble, so we're going to go ahead and plug in the inertia of the marble real quick. And we know that's 2/5 mr squared. I'm going to use little m, little r, and then alpha, we'll leave that for now. And then you can kind of see where we're going here. I'm going to do a little bit of algebra to simplify. And yeah, we're going to go ahead and do some stuff here. It should look familiar to you, right? So notice these r's cancel out, and then I'm going to also make a substitution. Guess which one? Oopsie, that's a 5. The substitution I'm going to make is instead of alpha, I'm going to write a over r, and we had that additional r there, so I'm just going to write a. So the r canceled out, right? So you have one r canceling out because it was on both sides. The other r canceled out because we substituted alpha for a over r. So now we have an expression for Fs 2/5 ma, and that's great. Remember, the problem with static friction is we don't have we can't calculate it directly. We don't have the coefficient in this problem, and even if we did, it wouldn't be equal to mu times the normal force because static friction is not like that. It can vary. So this is great because now we can make a substitution. We're going to take this guy and we're going to plug it into that formula up there, and we can go mg sine theta minus 2/5 ma equals ma. We'll go ahead and cancel out our mass now, and in the next step, besides canceling out the mass, I'm going to go ahead and add 2/5 to both sides, which is, of course, 7/5 a. So we now have g sine theta equals 7/5 a. Now, I know I mentioned this at some point in time. It's been a while, though. So the other thing they mention in the hints part of this problem, right, is use the small angle approximation. What is that? It's the idea that when a pendulum is swinging back and forth with sufficiently small amplitude, the sine of theta is approximately equal to theta. And this is just true of the sine function, right? So if you plug in, and remember your calculator needs to be in radians for this, but if you go ahead and put your calculator in radians, and we'll just, you can do this together with me if you want. I'm converting my, calculator's now in radians. So go ahead and type in the sine of 0.15, and notice that the answer is 0.14943881. It's 0.149. So the sine of 0.15 is 0.149. The sine of 0.08 is 0.0799. So basically, when the angles are sufficiently small, less than 15 degrees, then the sine of theta is basically equal to theta, and that's going to be relevant you'll see in a moment. It actually harkens back to one of the problems we did yesterday, because you totally did that yesterday. Good God, I've been working hard. You better be. Okay, so we're going to go ahead and make this approximation then. We're just going to say, you know what? The sine of theta is approximately equal to theta, so I don't have to write the acceleration as g sine theta equals 7/5 a. I can just write g theta equals 7/5 a, okay? And at this point in time, I can go ahead and solve for a, and I will, and then I get 5 over 7, and then g is in the numerator, and theta is right here. Now, this is particularly interesting for us, and the reason this is so interesting is because of one thing that we had said yesterday. And what we said yesterday was that the acceleration function was equal to negative omega squared times the amplitude, right? And we drew parallels between our equations, right? We said we have displacement and displacement right here and right here. And so if we make an observation, then we can see that 5/7 g is equal to omega squared. Now, if you can just work with me here for 1 second, I want to double check to make sure that what I just wrote is 100% correct. There we go. Yeah, okay, so that's correct, okay? So that is actually really important because what we're doing is we are establishing a way to get time involved. Okay, now you don't see a t here, but what you see instead is an omega, right? Now remember the omega, the negative sign here is not very important, okay? So even though there's a negative sign, we're not really super concerned about that. That just has to do with whether you're using sine or cosine, okay? So what I'm drawing a parallel to now is, remember that the theta is the amplitude of our oscillation with this marble, right? The marble's going back and forth like this. Theta is just the amplitude, because if the marble goes back and forth, there are 4 thetas per period. There's 4 amplitudes per period. So we do agree then, hopefully, that A and theta are both displacement and both amplitude, and that's critical because then I can go ahead and draw a parallel here, and that is that omega squared and A 5/7 g are related, okay? With that said, though, and I'll have to come back to this and perhaps explain exactly why this is the case, because to be honest, I hadn't really thought of this until just now, but we're actually not going to use A, we're actually going to use our alpha equation. So instead of using A equals 5/7 g theta, we're actually going to come in here and replace this equation with alpha, right? So if we're going to use alpha instead, well, remember A equals R alpha, and therefore alpha is A over R. So we're going to take this equation and we're just going to do 5g and we're going to divide by R, 7R theta, okay? Now, again, I'm not 100% certain why it is. I have to go back and check that, but we want to make this comparison here, not the comparison between acceleration directly. I'll have to go back and double check that. The short of it is, I believe for pendulums, you're always going to want to use alpha, but I need to go back and explore why, so I'll hit that up in another video. With that said, we can use this to proceed throughout the rest of the problem and quickly, actually, rather quickly solve this. So how can we do this? Well, the first thing we'll remember is that the period is 2 pi divided by omega. So there is a relationship between these two. And keeping in mind that we now draw the conclusion that omega is the square root of, and that'll be 5g over 7r. And by the way, actually, I just noticed a very subtle mistake. R is actually not what I wrote. I wrote little r. That's actually incorrect. Why is that incorrect? Because the amplitude of the oscillation depends upon big R, okay? So when we're trying to relate the acceleration in here, this angular acceleration and the linear acceleration for this bigger circle, we have to use the bigger radius. So I'm going to go back and correct that real quick. So instead of plugging in little r, I'm actually going to use big R. So notation very important, right? So big R there, okay? And so now that we have all big R's, we can go ahead and write our formula for this. So substituting in, if I'm going to plug this guy in there, I'm just going to flip him. So I get 2 pi square root 7r over 5g. And if I do this calculation, whoopsie, then I can plug in what I know, which is 1/2 meter. And I can plug in 9.8. And let me just quickly double check that I did not make any silly mistakes and make sure that that comes out correct. So 7 times a half divided by 5 divided by 9.8. Take the square root of that. Yep, this is looking good. Multiply by 2 pi, and yep, we get our answer, which is 1.68, or about 1.7 seconds, okay? So that was a lot, and it was kind of quick, so I'm just going to quickly recap what it was that we did and how we got the answer to number 10. So I know this, I asked you guys to do number 10 here, or I was going to ask you to do number 10, but this is such an interesting problem, and it's illustrative, and probably would have been really challenging for you guys, so I figured I'd do it as a group here, almost as an example. So instead here we have, once again, this marble going back and forth is analogous to this idea of a pendulum, with the primary difference being that the marble rolls, whereas the pendulum bob does not. So with that in mind, our general approach was Newton's laws. We wrote equations for our net force, so this was F net, right? And we wrote an equation for a net torque. So critically, those were 2 big steps. And then after we did that, we got an expression for our acceleration at this part right here. Once we were at our acceleration, we made an approximation. So this is an important step here to understand that we went from sine of theta to theta, because that is small angle approximation. So it's kind of hard to fit that in here. I might just go ahead and erase a bit here. So we had, at this step, there was a small angle approximation, very important. So with that in mind, once we had our small angle approximation, then we recognized, and again, I'll have to go back and convince myself of why this is true, but we do have to compare the pendulum's angular acceleration and its angle theta. And that honestly, that I actually just thought of this. The likely number one reason we have to compare these 2 equations here, right? The reason we probably have to compare these 2 instead of these 2 is because of the fact that this is an angle. In other words, it's an angular displacement, and this is an angular acceleration. So that's a pretty good justification, I think, for why we'd want to compare alpha and theta to A and amplitude, acceleration amplitude. In any case, once we've made that comparison, very, very important, then we make this critical realization that our angular frequency, omega squared, is going to be going to correspond to the 5/7 G over R. That's very, very important. And this, honestly, like, if you take anything away from a problem like this, it's this relationship right here. This is so critical. And the reason it's critical is because it allows you to go from understanding acceleration to time. And remember, we can't easily do that in the circumstance of a pendulum, because the acceleration of that pendulum is changing, right? So we know that if we have acceleration and we want time, we can use kinematics. True if the acceleration's constant, which it's not here. So this is why it's so critical that you draw this comparison between omega squared and our the angular acceleration formula. So remember, that comparison is drawn from the fact that amplitude, theta is the amplitude, right? So we have all these arrows all over the place now, but theta is the amplitude for this system, and that's very, very important. So then we can immediately draw the conclusion that omega squared is equal to 5/7 G over R. Then we just use our period formula and we're done. So that's this example. I'm going to go ahead and shut up. I'll be posting a few more problems, but this should be an illustrative example. I would strongly encourage you to work this through yourself at least once or twice maybe, and in best case scenario, study it and then go back and try to replicate it without my help. And if you can get to there, you're doing well. So I'll be posting again later today, guys. Thanks.